Okay, here's so this is like
Yeah.
moving, yeah. Here. Yeah, this in here.
No, it's okay.
Put it
No.
in. No? Those things are always, I always like losing it.
Yeah.
Actually, I'm not from Ontario. But I grew up. No, it's still mainland. So,
Oh, yeah, so you're right there. I see. Okay.
but I grew up in Hampton, which is cold. No, it's like very. That's a yeah. No. Yeah, it's
Still need the rest of your restoration. Still need to make
the mountain tree and all that. Really? Are you gonna show this? It's insane.
Yeah.
More fine. Well, they were. I don't know.
I haven't driven across the border in many years.
Okay, should we? Okay, I will keep another 30 seconds and then we're going to start. We can start with our afternoon session with Professor Levitov. Continue from the Monday. Here is.
Yeah, thank you. Okay, good. So good afternoon, and I will basically tell the same story as you heard already. One more time always helps, but maybe now focusing on experiments rather than on theory. That's the plan. But I mean, to recall what we talked about last time is that if we have a two-dimensional Fermi surface and there are carriers scattering on it, quasi-particle scattering on it in a momentum-conserving way, then because of collinear collision constraints, the processes that dominate head-on collisions, two particles coming in and head-on going out also the same way. And so in this case, what we discussed is that there are many surprisingly slow modes that have odd parity under p to minus p symmetry. And because of these slow modes, one needs to extend the hydrodynamics and construct hydrodynamical description that doesn't restrict us only to current and particle density, but includes also these other slow modes, and there is a whole hierarchy of these. We discussed what they are, and that hierarchy they have temperature scaling, which is not what is expected from Landau theory, and so on and so forth. So yeah, so we will, yeah, I mean, talk about that. Yeah, so the multiple slow modes. So what we want to understand next is how these modes contribute to observables, conductivity, viscosity, and other things. And so we want to, I mean, want to solve for dynamics in which the excitations are dominated by odd parity shape deformations of the Fermi surface, such that all even parity modes, relaxed quickly, and we're interested in long time scales when odd parity excitations are the ones survive. And generic odd parity excitation, we can either understand it by taking odd parity harmonics and their linear combinations. That's what we discussed last time. Or one can just, take a general distribution, which is odd parity under P2 minus P, and then ask what these I mean, they're of course equivalent to what we discussed for the odd parity harmonics. I mean, you can do Fourier transform on the angular variable and get odd parity harmonics as before. But I mean, this is maybe more general. One thing you see from this picture is that these odd parity harmonics that happen to be the long-lived excitations, they can carry current. You see that, I mean, every particle pocket added to the surface is because of P2 minus P is accompanied by a whole pocket on the opposite side, and so the contributions to current of particles here and the hole there will double, and that's a general fact. So these odd parity modes will be contributing to current and to conductivity and to transport, and dominate in that. And because of that, it's interesting to study their behavior. So that's comment number one. Comment number two is that we're not restricting ourselves to we coupling. We're allowing any kind of two body interactions and any kind of so based on what we discussed last time, the picture is generic. Also, these collinear constraints, they are not really special for perfectly circular Fermi surface. They're also applicable to any non-circular Fermi surface, so long as if it's convex. So shape deformations are not a problem. Imagine an ellipsoid, and if you take an ellipsoid, then everything we talked about will apply nicely. Any other convex shapes will be okay too. So that's kind of summary of what we discussed last time. Okay, and so if there are questions, please stop me and ask.
Yes.
Yeah.
Can you define what tomographic dynamics?
Yeah, so tomographic means that it's P2 minus P collinear. I mean, the main processes are happening along the rays. I mean, there is some angular broadening because of temperature, but mostly it's happening along the rays. So it's very much like an I mean, other kinds of tomography, in particular in medical tomography. When you do X-ray tomography, that's exactly what they do. So signatures of hydrodynamics. So as we discussed last time, I mean, the key signature is that collisions help transport. And so if we're in a hydrodynamic regime, resistivity as a function of temperature drops rather than doing otherwise as it happens in the metal in the presence of phonons. So here, collisions, particles passing momentum to each other help conduction. And so we want to understand that, and using the microscopic theory, microscopic picture we derived, understand that. So typical experiment and typical data, and this is referring to that paper that we wrote a while back with Hao Yu. looks like that. I mean, one can make an experiment transport measurement through a constriction, and this is a depiction of a real experiment that people did on graphene. They etched graphene to make constrictions, and then measuring current, passing current through it, measuring voltage. You see that the linear resistivity, it's fully in the ohmic regime, no nonlinearities. The linear resistivity as a function of temperature drops over first 100 Kelvin and then starts to grow because phonons kick in. So that's the signature we're talking about. And then different curves here correspond to different carrier densities. I mean, there is a big gate that with which you change doping, and so you can change carrier concentration. And so the material in this case was graphene monolayer, but then later people have seen it in other material, in two-dimensional electron gases, let's say in gallium arsenide, and we'll see that shortly. But I mean, the key thing you see is that temperature dependence is negative. Yeah, that's the thing that we should focus on and try to understand. Yeah, maybe before we get to that, I should say that viscosity, I mean, even before you get to thinking about electrons, if you think about gases and viscosity in gases, it's also a very interesting subject. And there are surprises there, and I mean, there are surprising behaviors with viscosity of gases that this person, Knudsen, Martin Knut Knudsen, Danish physicist, discovered 100-something years ago. So these things which he discovered, I mean, they're surprising, and then from my experience, they happen, to come back and surprise people again and again. So maybe it's worth talking about for a little bit. So Knudsen studied gases flowing through pinholes, and then as a function of temperature or as a function of gas density, more likely. I mean, you see different regimes. You see regimes when at high density particles collide with each other, rapidly, and basically you see a viscous flow through a pinhole. And then at low gas density, collisions between atoms are rare, and so the main mean free path by which particles lose momentum is due to particles bumping into pinhole boundaries. And so the behavior in these two cases is quite different, because in this case the mean free path for losing momentum is basically diameter of the pinhole. Here in the viscous flow, it's more interesting because here particles collide with each other rapidly, but these collisions are momentum conserving, so you don't dissipate collisions by this process, and as a result, the main dissipation process is still colliding with the boundary, but then each particle individually will take it much longer to diffuse to the boundary, because maybe I can sketch it here. So in this experiment that we're interested in, when something is flowing through constriction, and this is the flow, if you look at an individual atom, then on the left side, when it's a viscous flow, individual atom will execute some diffusive trajectory with each line corresponding to mean free path before colliding with some of the atom, and so it can take it through the flow, it can take it through constriction, and there are collisions, but momentum isn't lost in the process, just passed around. So these collisions are not dissipating momentum, period. The only thing that can happen that dissipates momentum is when, this particle comes to the boundary and then collides with the boundary and then continues, but then here momentum is dissipated. So, the thing that we should have in mind is that when you have a viscous flow just from this, you can tell that the rate of momentum can either through the system without dissipating momentum, and will be longer. That means that the rate of momentum dissipation will be longer. Therefore, Knudsen observed that hydrodynamic pressure is lower than the lower gas density, because the lower gas density, I mean, the same thing happens. I'll draw it with a different color. If particles are moving freely, it may collide maybe with a gas, and next time it will collide, then we'll lose momentum to the boundary, or some particles will not collide to the boundary at all. And so most of the particles, larger particles that through the pinhole collide with boundary, than in the viscous flow regime. And because of that, dissipation in this dilute regime is higher, and hydrodynamic pressure will be higher. And so this is, it's surprising, and we know about it very well from StatMech. I mean, I learned about it being an undergrad, but this keeps coming back and surprising people again and again. One instance of the kind is that, some time ago, maybe 10 or already 15 years ago, a colleague of mine walked in my office with his eyes like this, and he's an esteemed experimentalist, and said that we discovered something amazing. I mean, we have a helium flowing through a pipe, and we discovered that we increase pressure, hydrodynamic pressure drops, and we thought that there is a leak, like a week, another week looking for a leak. We don't want to lose helium. Eventually discovered what helium is doing all by itself without, and what we had a discussion, and turned out that it's just Knudsen thing. So, but I mean, this is not just one instance. I mean, I see from experience that people run into this again and again and are surprised. So to describe this, I mean, as we said already, Knudsen introduced this number, mean free path divided by system dimension, and if this Knudsen number is greater than 1, the flow is nearly ballistic. Particles go through unaffected, and if it's much smaller than 1, it's viscous, and then there is this intermediate regime that people often define. But that's the idea, and so this is surprising, and in fact directly related to what we're talking about here, because we have this viscous regime. I mean, at 0 temperature, we have ballistic regime, which is very much like what I tried to picture in red. And the ballistic regime is also interesting. We'll talk about it shortly. But when you raise temperature, collisions become more frequent, and then because of that process and particle collide with each other, make them reach boundaries where momentum can be dissipated less frequently. And then it can flow through with less resistance. So that's that's interesting. So electrons kind of self-lubricate. You can say it in this way. They self-lubricate. They shield each other from unwanted effects of the boundaries, and And that's this Knudsen effect, essentially. Or, I mean, in case of electrons, this was introduced by Gurdjieff, and so it's called Gurdjieff effect in electrons. But essentially, it's the same thing as there, but applied to electrons. And yeah, so in the case of electrons, I mean, people make constrictions like that, defining regions where electrons can flow using gates, and then measuring transport, and that's what you see. So the interesting thing here is that if you don't worry about phonon part, the high temperature part, at low temperature you see essentially linear temperature dependence, and that's surprising because collision rate, naively collision rate, as we discussed last time, would be t², but here you don't. And then if this was a three-dimensional system and you make a three-dimensional pinhole just like Knudsen and try to push helium through it, then it would basically look the same way. There would be a negative temperature dependence on resistivity, but temperature dependence would be t². In helium-3, this was thoroughly studied and documented. But here it's linear in T, so that's interesting, needs to be understood. So that's what people saw in the early experiments on graphene. Then later it was reproduced. I mean, experiments were done on a system which was in a way even cleaner, the two-dimensional gallium arsenide electron gas, where they made constrictions. Actually, this is taken from that paper, from ETH group. And so there they found basically the same thing, linear T dependence, and yeah, so now it is pretty much established, needs to be understood. And maybe, what else is here? Yeah, and so what we're going to talk about is how this is explained by this tomographic transport picture. And we already introduced that last time, and we'll talk about that again. Yeah, so this is basically what the story is going to be. And yeah, we already talked about that and about that. And so yeah, so now our problem is to study conduction due to shape modes of Fermi surfaces. And yeah, before we jump in, maybe stop here and see if there are any questions.
Yeah, the experiments from the previous slide, I mean, it's all still linear response, Stokes ohm.
Yeah.
What kind of current?
I mean, in ohmic regime, very small. Current is very small. I mean, so if you go to high current, then they also observe something, and that's interesting. I think I mentioned that at the beginning of my talk on Tuesday, but let's not get into that. I mean, let's just follow Knudsen steps. We'll be doing linear response. Yeah. Other questions?
So Knudsen flow was like showing that the gas, which is like just the neutral, charging neutral particles, and then see the similar effect in this, like the reduced dissipation due to electron collision. But then the electrons, like Coulomb interaction doesn't do anything.
And the Coulomb interaction is what leads to collisions and viscosity.
Similar thing happen, in this like just the gas particle. Then that's just the head-on collision when you consider. Is that how?
Okay, in there is no head-on collision constraint because in 3D collisions are not required to be collinear by kinematics. If one would make a gas, Knudsen didn't do it, but these days in cold atoms people could do it. One would make a gas of neutral particles and try that. I mean, sure, same thing would happen. Yeah. Yeah. Good. So let's see. Yeah. So this is just a reminder of what we talked about last time. I mean, you can take the shape modes the shape modes that we introduced, and then ask how quickly they relax, and find that even parity ones relax quickly and odd parity ones relax more slowly, and they scale with temperature c squared and t to the fourth respectively. Yeah, so I was showing last time our calculations, but I forgot to mention that this was also seen by other people in this paper, and so now this is pretty well established. So then, I mean, to get to actually explaining the behavior we're interested in, maybe let's start with this picture. So if I take these different modes and try to sketch their lifetimes or rates of decay for as a function of angular momentum for different temperatures, and scale everything to Landau rate, scale everything to t-square rate. So all the rates will be divided by the Landau base rate, and then the odd parity modes will have temperature dependence, which is t to the fourth. Also, they will have dependence on angular momentum, which is m to the fourth. And because of that, as you increase the angular momentum, I mean, at a fixed temperature, let's say we take a relatively high temperature, the odd parity modes will have longer lifetime, but then as you increase angular momentum, it will quickly become comparable to the even parity modes, and then I think that beyond that point, modes become indistinguishable. If I take a lower temperature, this one, then I mean t to the fourth growth will also happen, but then it will take longer for these modes going to higher m to reach the even parity rate, and so there'll be more of these very slow modes, and then if you go to even lower temperature, there will be even more of them. And so what we're interested in at these low temperatures is the contribution of these modes to conduction. And each of these, I mean, if I'm very naive, I can say that let me take one of these modes and try to derive some kind of diffusion equation for it, which one can do, and you can see using this diffusion equation, we see that these modes propagate with effective diffusion coefficient, which is of a normal scale. We'll talk about what it is in a second. And then if you ask, what fraction of these modes are important, which of them can go through the system quickly enough without losing their momentum. Basically, that's the region shaded in pink. There will be more and more of these modes at lower temperature, and it turns out that it's this process that dominates. Sorry, not this process, but this counting that dominates the behavior. Because originally, I mean, to be honest, we were a little surprised. We knew that there are these rates which scale as t to the fourth, but it wasn't clear how t to the fourth gets converted into T-linear behavior. So one might naively expect that there'll be a t to the fourth and resistivity, but actually it's not like that. What really is going on is that this t to the fourth and m to the fourth makes the modes behave so that there is more and more of them that are actively contributing to transport, and as a result, the number of active modes grows rapidly with temperature, and that's how conduction happens. Yeah, so that's a qualitative picture. Maybe can try to make it more precise, but maybe if there are no questions here, if there are.
How do I see it? How do I see it to the power 4?
Yeah, so as one of my friends says when he wants to annoy the audience, he says it follows from the analysis. So okay, so let me try. So actually it's not so simple to describe. So it turns out, I mean, one can do it more, more rigorously. But before we do that, let me just explain qualitatively what's going on. So this is the paper. No, it's not this one. It's the paper that we wrote with Howard Yu and Patrick Ledwith. That if you take a two-body collision, maybe let me find a picture suitable for that. Yeah, if you take a two-body collision, and then naively you would say that actually shouldn't be thinking about this collision, should be thinking about these ones because these are dominant. You should say just find the rate of these collisions, and then there will be some angular broadening at finite temperature, and then just take that angle, which is of order t to 2e Fermi, and then say that the whole process will be a random walk with that angle. So there will be, yes, there will be some angular relaxation, but it will be a slow one with with angular diffusive process with angular step of temperature divided by Fermi energy. So that turns out to be that's this paper. Actually, the last one. Turns out to be wrong because it turns out that if you think carefully about kinetic constraints, what's going on is that the movement in the angle is back and forth. So every time it moves in the angle one way, then on the next step it moves in the angle the opposite way, and to linear order in temperature, these angular displacements are exactly to linear order, they're equal. And as a result, the angular diffusion doesn't happen. Angular diffusion doesn't happen, and the leading contribution is correlated angular diffusion. If you go right, in the next step you're forced to go left. Because of Fermi statistics, basically, and that's how that emerges. But now this and that's the qualitative picture that is in that paper, 2019, and then later, I mean, people did simulation, calculating it explicitly. Turns out that to be what this qualitative argument gives is exactly right. Surprisingly, maybe. So then, good. So then, let's see. Stopped here. We should just see. Yeah, okay. So we're here. We need to talk about this. So to proceed and to understand conductivity and viscosity in this regime, I want to maybe go back to what we discussed when we talked about this relation. So we discussed, I mean, we talked about how this can be derived. I mean, we can do it on a chalkboard, or someone can do on the chalkboard, to remind ourselves what we did here, and then because there is the general result for conductivity in non-local conductivity expressed in terms of rates, relaxation rates for different harmonics, we can try to use that to actually understand T-linear behavior. But maybe just to set the stage, maybe let me start with reminding you how we get non-local conductivity. I mean, in a simple model, when there are no long-lived excitations, I mean, which wouldn't be correct for this problem, but it's something that you often see in the literature. So I think it's useful to put it on the chalkboard and put it on the board and then compare with it. So if I let's see. So what's the trick to make it go? Yeah. I see. So they, okay. Yeah, now we can write here. Yeah. Okay. So there is this Stokes-Ohm model. Stokes says that take Navier-Stokes equation and add momentum relaxation to it. The field will look like this will be momentum relaxation rate, and then that will be diffusion term, Laplacian of V equal to E times N times electric field, something like that, right? And then I think I want to, yeah, so I just want to, I mean, so it's written like that from second Newton is equal to electric field. If you write it for, then you get E over N and over M, where N is particle density, M is particle mass, and so you get this equation, and then from that you can tell that particle current, if I calculate it, say that I'm driving it with varying as e to the IKR frequency omega, then this will give me current oscillating at frequency omega wave number k, and this will predict conductivity. Function of k of omega is going to be, let me write it first in full way, n square over m, and then there will be 1 over gamma p minus omega plus eta k square. Yeah, so we'll look like that, and so eta is viscosity, and gamma p is momentum relaxation rate. So this is pretty much Drude conductivity that you saw in 2 talks today and many talks before then, with viscosity coming in as additional momentum relaxation rate, which is what viscosity does. Because viscosity is essentially momentum diffusion rate. And so high momentum diffusion allows electron to bump into boundaries more quickly. And so high viscosity means that there will be a higher momentum relaxation rate. But then also there is this K dependence. K dependence is telling us is that in the case of viscosity, you only get anything interesting if there is a shear flow. If there is a uniform flow, then there is no momentum flowing anywhere. Only if there is a shear flow, something flowing. So the K dependence is essential, and we have that now. So now if we have that, and I have let's say this geometry that we introduced and current flowing through it, then in order to find conductivity in a Stokes-Ohm model, I would what would I do? I would just say, let me take the conductivity and set K roughly of the order of the width of the system, call it W, 1 over W, and then that with K being over the W would tell me what conductivity is. So let's say I have no momentum relaxation, so gamma p is 0. I'm doing static case, so frequency is 0. Then conductivity will scale as W square of the width, right? So that's unusual. You take system, have ohmic transport in the system with W, then current will scale proportional to W, and here it's scaled as W square. And that's exactly that effect that momentum dissipation slows down in the case of diffusivity, conductivity becomes higher. Yeah, so then, I mean, that's the story, and one can get temperature dependence if you take this rate. And let me remind you that in kinetic theory, viscosity is equal to V square Fermi gas, will be V Fermi square divided by gamma with m equal 2. So that's the relaxation of the ellipsoidal harmonic, this one. If you open any textbook on kinetic theory where viscosity is derived, you see that they derive this equation, factor 4 here, that I need to write. And so this will be expressed in terms of ellipsoidal harmonic relaxation rate. And for ellipsoidal harmonic, we know that it's not anything usual. It's just ellipsoidal harmonics relax with the m equal 2, so they relax with t square rate. So one can ask, I mean, why are we interested in odd parity rates? The reason we're interested in odd parity rates is the following, that these are, I mean, if you look, I'm not sure how much time we have. Yeah, maybe let me not, I mean, we can, if anyone wants to see how this is derived, we can do that. But if you just trust me on this expression, we derived it last time, just allow me to use that. Then this expression looks like Drude conductivity. And then here, instead of, here there is a k-square dependence, but then this k-square dependence is divided by a whole monster of a continued fraction in which it starts with gamma 2, and then z is k square, z is the wave number square. So naively, I mean, if I say that, let me take the long wavelength limit, small k limit, as I'm supposed to do when I derive the hydrodynamic behavior. So just take that and then set k to 0. Then all of that goes away, and then I get gamma equal 2, and I'm in agreement with Navier-Stokes with the Stokes-Ohm model. However, I mean, if you now consider a limit just out of curiosity, in which, let's say, gamma 3 is enormously small, let me just set it to 0 for fun, right? Then in this case, so let me consider the case when gamma 3 and gamma 5, etc., gamma 2m plus 1 are equal 0. So they are enormously small, allow me to ignore them. Then what happens, you can kind of see it just by staring at this expression. If you remove gamma 3, then the two levels of continued fraction cancel one another, and then you get instead of that you get an expression in which you have gamma 2 plus gamma 4, and then this one also disappears, and then you get an expression in which gamma 2 is replaced by gamma 2 plus gamma 4 plus gamma 5, and so in this case you end up with gamma 2, same expression, but gamma 2 is being replaced with gamma 2 plus gamma 4, gamma 6, etc. And so it continues until where we stopped. So it will be gamma 2m plus 2. Right? So in this limit, if I ignored odd parity harmonics, you see that your conductivity kind of preserves its form if you don't worry about the long tail of continued fraction, but gamma 2 becomes bigger. Instead of gamma 2, you get more terms now. Replacing gamma 2 by a bigger number means that viscosity dropped, and then because viscosity is momentum diffusion, it means that if viscosity dropped, it means that dissipation, the rate of dissipation dropped, and that means that conductivity went up, and it went up by a factor which is of order 2m plus 2, and then where exactly I will truncate it, will depend on temperature. So there will be a the other way. There will be a temperature-dependent amplification of conductivity, and you can say that adds. I mean, if you do like full analysis, you find that your instead of t² rate, you get t² times 1 over t, because 1 over t is how that added effect scales with temperature. So that's a crude explanation. I mean, one can do more analysis, but roughly that's where the anomalous temperature dependence comes from. You just get more of the long-lived modes which are relevant, and that's kind of the idea. I'm not sure if I'm explaining it well, but I'm just trying to translate what this. Yep.
Can you go to that slide again?
Here? No.
No, yeah, that one. So it's something strange. So, well, first, if you just do one level of that hierarchy,
Mhm.
then you get this equation that you derive this conductivity. How do you go to the next level? I don't understand. Is this equation, is it beyond this equation? Or is it still within this?
No. So this equation is what one can derive. There's no approximation made. This is like what we derived exactly from linear response. I mean, we can go back to that and look. So there is no approximation made. But
Is this equation follows from this Stokes Ohm's model or not?
No,
It's beyond this model.
it's beyond this model.
Okay, so can you remind us how to iterate? I've forgotten. How do you go?
No, I mean, sorry. I mean, there are no specialists here, so I don't have to apologize. What I'm saying is that Stokes Ohm model is not applicable to the fermions. Junk.
Okay, so for p equals 2, you're getting that form, but if you want to go further, you need to do what?
Yeah, I need to do the right thing. So the right thing is what we derived. It's linear response, current linear response expressed in non-local conductivity, and non-local conductivity will have contributions from all modes, from all relaxation rates. And then what I'm trying to explain here, maybe not in the optimal way, but that if you have some odd parity rates which are anomalously small, so that I can just ignore them, that will increase. It will suppress viscosity by a factor of how many these odd parity modes I have, and suppressed viscosity means higher conductivity, because conductivity is inversely proportional to viscosity. I mean, you don't need to use words. I mean, you can, because this is exact thing that we derived. We can just study it and do it. Do full.
Each one of the each of the odd gammas is an odd function of m, and m to the fourth.
Yeah.
T to the fourth.
Yeah, it's a function of m.
But the even ones are t squared.
Yeah.
That's the series I need to sum.
Yeah, you need to sum continued fraction with these rates. Yeah.
With m to the fourth, and then
yeah.
But the even one doesn't depend on m and t squared.
Yeah, pretty much. Yeah.
Okay.
I mean, I say pretty much because if you look at in the papers, I mean, some of them say that there are additional logs. So the scaling that I wrote is m to the fourth. The Sarma paper says that m to the fourth log m, but we don't care on that level. We don't care.
But this is all, I mean, DC transport still captured by.
Yeah. Yeah. So then, but I mean, because we have an exact expression through these relaxation rates, one can simply do the analysis and plot, let's say take continued fraction, by the nature of continued fraction structure converging pretty rapidly, so you can evaluate it, even though it's an infinite continued fraction, it's not hard to evaluate it, and then you plot conductivity as a function of, k, for different temperatures, and you see right away that if you increase temperature, so let's see, so if I look here, there'll be three regimes that two of them are the ones we expect. I mean, there'll be ordinary hydrodynamics at very small k, long wavelength. So that happens when we really go to like 0k limit. So we can ignore, because k is so small, we can ignore all these relaxation rates, which are high m. So in this case, evaluating continued fraction gives me ordinary Ohm-Stokes behavior, and then if you go to high k, very high k, you get ballistic behavior, because at high k, short distances, collisions are not important, and you see ballistic behavior, and you can get the same thing from continued fraction. So your quantity that you evaluate becomes linear in k, and you see it here. But then in between, you have some other power law, and if you try to draw a line here, then it will be k to the power 1/3. And so there is some anomalous scaling that one can study. And so if you try to fit conductivity to a power law, then unlike what you have here, so here you would predict that conductivity scales as 1/k². And then this scaling tells you that conductivity fits closer to 1/k to the power 5/3, right? But one can also, take it as a math problem, do it to undergrad, and the undergrad will derive it. I mean, it can show you, yeah.
Does this law of 1/k to the 5/3 follows from the continued fraction formula?
Yeah.
How does it follow?
Yeah, so one needs to, one step at a time. One needs to do. I mean, I can sketch it maybe here. I can show the analysis. So basically, I mean, if you look at this expression, then you see that the quantities that are interesting. The quantities which are interesting that you want to understand are partial fractions. You want to define, so scaling continuous fractions. So you derive these quantities, partial fractions, take partial fraction truncated at some level, gamma m plus z over gamma plus 1 plus z, gamma m plus 2, etc. So it turns out that because we want to study the problem in that range where there are many anomalously small rates, but then they eventually grow and merge together into a rate that is blind to even and odd effects. The natural way to do it is introduce these partial fractions, then study how they vary with m. And then if you do that, you can do the analysis follow. So there are several steps which are kind of obvious, and I have it sketched for myself before this. Before we started, you do yes, so you want to understand how this varies with m. Now, at large m, where the rates become equal, it's very easy to evaluate because if this is some constant rate, I mean, we can evaluate continued fraction instantly. So we really want to understand it in this pink region, and then in that pink region we define this, and we can take that and try to derive a discrete differential equation that relates it. So you first of all, one observation you want to make is that you are not so interested in even m. You're only interested in odd m because even m should be somehow integrated out. I mean, the good way to do it is to take this relation and then iterate it twice and then derive a recursion relation for m plus 2. So with m, so this allows you to relate m and gamma m plus 1, and then repeating it one more time, you do that, and then if you plug it in, you derive something like one gamma plus 2. So I'm writing a horrible expression just to impress you, But I mean, it's also true. But you will see now why I'm cheating a little bit. Yeah. So this is a correct expression, but then, I mean, you notice that if you use an ansatz and write gamma m as z over gamma m minus 1. Yeah, I'll explain in a moment where this ansatz comes from. Initially, we just guessed it without understanding where it comes from, but or more precisely, the undergrad guessed it. But then, if you plug it in, you find that now for these variables you get linear difference equation. So it looks like plus 1 plus m minus 1 minus 1. No, sorry, equal, correct, yeah, correct, equal gamma plus gamma m plus z over gamma minus 1 plus z over. Yeah, you get something like that. I mean, I mean, clearly, more easy to deal with than this nonlinear equation because this is linear, and it looks like a difference equation. However, in the regime in that pink region, where you expect that there are many of these interesting variables, and they are varying as a function of discrete m sort of continuously. You can pass from discrete domain to continuous domain, and then replace differences with derivatives, and after you do it, you get a Bessel equation. You get a Bessel equation for Bessel function with index 1/3, and then you solve that. Then using the solution for Bessel equation, basically integrate that from high m, where nothing interesting happens, all the rates are even odd rates are the same, down here. What you're interested in really is gamma at m equal 1, because that allows you to compute current. So you integrate over that using that discrete Bessel equation that you transfer to continuous domain. And the only input I forgot to say is that we do it for with m to the 4th. So with that and that, you get Bessel equation that you solve, and then everything else is very simple. I mean, the details are in this paper. So that's kind of how it. I mean,
This paper, right?
yeah. I need to. Yeah. Anyway, so the. Yeah. So it's interesting. I mean, you get linear T dependence basically from the counting of how many you get that contribute. I mean, they're long-lived, and also they're propagating. So they enhance conductance because of this argument we gave here, and want to know how rapidly that enhancement changes with temperature. And then from this analysis, you find out that it's linear. So this T square, Fermi liquid T square, is replaced by that's the story. And so you get the scaling for conductivity versus wave number and conductivity versus temperature. So then you can plot it against experiment. I mean, you can take these theoretical curves, and then maybe one thing I forgot to say is that if you take this approach, continuous fraction approach, we can derive it not only for electron-electron scattering, we can derive it for any kind of scattering. If you're, let's say, if you have electron-phonon scattering in the system, you can include that. If you have disorder scattering, you can include that, because gamma m's are just rates, relaxation rates for different harmonics. So you can easily adapt it to, to describe electron-phonon scattering. And so if you include electron-phonon scattering at temperatures higher than Bloch-Green-Eisen temperature, then you see temperature dependence similar to what experiment shows. There is a linear T dependence at low temperatures, and then it starts going down roughly around the Bloch-Green-Eisen temperature. Not exactly, but I mean roughly there. So you can match it to experimental curves. Yeah, and so the picture. Sorry, let me just check. Yeah, good. Yeah, so that's the end of that part, and I mean, please ask questions. But then the picture is that there is this interesting transport regime in which there are, instead of ordinary momentum diffusion, you have this more complicated behavior in which particles collide head-on, and when particles collide head-on, as we discussed last time, you get hole propagating back, and that hole propagating back collides with a hole, and then propagates forward. So the whole transport is a result of that process, which is distinct from that process, from the ordinary momentum diffusion process, and that eventually contributes to to anomalous power laws. You can think of it as a cascade, if you like, and one maybe nice way to say it is that at low temperature you generate many of these long-lived excitations that dominate in this transport regime. And I mean, what we found for the purpose of evaluating conductivity is their cumulative contribution to conductivity. But to some other quantity, they will contribute in a different way. The underlying fact is that there are many more of them than you would naively guess based on Stokes' own picture. So you generate these many long-lived excitations, and they dominate in this region, and then they scatter with each other and contribute to transport in this strange way. Incidentally, I mean, the power law you have here, 5/3, coincides with Kolmogorov's scaling for turbulence, but I think this is sheer coincidence. There's no reason, no deep connection as far as I can tell, but interesting. and it's exact.
But at least qualitatively, is it possible to understand why this power appears here, k to the 5 thirds?
I don't know a simple argument. I mean, so for us,
From these derivations.
yeah, so we just, I mean, we derive it, but also we see it, you know, see it like that, just taking the k dependence that we predict from that exact formula, and it fits. But I mean, if there was a simple hand waving, or maybe even not so hand waving explanation, that would be nice to know. Yeah. Anyway, I think we're spending too much time on that. I mean, should stop in half an hour, and I have so much to talk about. Yeah. So, okay. So we answered all the questions. Yeah. Then maybe continuing on experiments. I mean, one can ask, are there other ways to actually see the long-lived modes? And so what we talked about so far was their cumulative contribution. We know from this discussion that there are many long-lived modes, and they're there, but it would be nice to see them individually and kind of probe them one by one. So one way to do it is to use cyclotron resonance, because if you apply magnetic field and you excite cyclotron resonance in magnetic field at the energy equal to separation to m times cyclotron frequency, then you excite into mth harmonic. So if you do cyclotron resonance at a frequency which is multiple times cyclotron energy, then you excite for m equal 3, you excite into third order harmonic, and fourth order, and so forth. So in cyclotron resonance, you can excite these harmonics individually. And then from the width of the cyclotron resonance, one can predict, you predict that the odd parity resonances will be more narrow than the even parity resonances, and you can predict the t dependence. So that's the plan. And so this is something that we're working on, and there are people with whom we had many useful discussions, and some of them maybe are even going to do this experiment, and there are all the capabilities for that. So that's the idea. So you can see, you definitely can see even odd effect for sure. Seeing temperature dependence probably a bit more problematic, because in cyclotron resonance you heat the system, and whether electrons will have the right temperature is a bit of a question. But I mean, with some care, probably temperature dependence can also be extracted. So anyway, so that's the plan. And if you now start solving this problem, I mean, you run into various issues. So first of all, if you are exciting cyclotron resonance, basically you're exciting magnetoplasmon modes, and you are interested in high order magnetoplasmon resonances. And there is quite a bit of literature on that, and various issues that this literature resolved, in particular the Fermi liquid effects and how they renormalize these magnetoplasmon modes. And what we know is that if you have Fermi liquid interactions, then magnetoplasmon mode is renormalized up by Landau function. And so that's a result from that paper. I think it was recently re-derived in several other papers, including Andy's paper. But I mean, after that, the interesting part only begins, because then you want to apply it to actually studying how different resonances broaden. resonances broaden. And what you find in the process is, A is an even odd effect. Odd parity resonances are more narrow than the even parity resonances. And then the other thing you find is that there are interesting Fermi-liquid renormalizations of different resonances, and you can derive express it in terms of angular harmonics of Landau Fermi-liquid function, and so then you're coming to actually question how are we going to probe it. So in different experiments, I mean, you have constraints due to how your excitation field is varying in space. And if you are, you have to decide where you want to be. You can be in the situation when your cyclone orbit radius is much larger than periodicity with which your excitation field varies, and then you have averaging over plus and minus sign excitations over that orbit, and that's not optimal, but unfortunately this is more common in experiments. You want to be in this regime. When your excitation field is nearly uniform. It's harder to realize, but I think technique is there. And yeah, one can do all the algebra, and I don't want to spend time talking about that in detail, but you can basically do the same analysis as we discussed last time, but with magnetic field now. And if you do it with magnetic field, your optical conductivity also will look like a continued fraction, but continued fraction, a different kind of continued fraction. Now the rates will be shifted by m for gamma m will be shifted by m times cyclotron frequency, and but then I mean play the same game pretty much, and then from that you can derive optical conductivity, compute absorption, and after you compute absorption, you get broadened by temperature dependent in a temperature dependent way, and so this is a typical dependence that you see when you do this calculation. There is so this is the main resonance on the main cyclone frequency at so z is a wave number squared. So z so this corresponds to excitation field which is nearly homogeneous to inhomogeneous, and so you see that what we just discussed actually is working. You have a very nice effect when it's nearly homogeneous, because here you see a very narrow, all of a sudden you see a very narrow third harmonic. Odd parity harmonic shows its natural width. If you are in this spatially, if you are in this less homogeneous case, then there will be additional broadening of harmonics because of that, and then you lose the interesting effects. So you want to try to avoid it and be in that regime. So for that you need to have some control over how inhomogeneous, or more better to say how homogeneous your excitation field is, yeah. So that's kind of the story on the theory side. Maybe let's stop for a second and see if there are other questions, because I have some experiments to show. Yeah.
One question. How does the cyclotron resonance couple to the Fermi surface harmonics at a microscopic level?
I mean, so if you are doing it at cyclone frequencies smaller than Fermi energy, you're only exciting states near the Fermi level, because your energy is not enough to excite from deep from the Fermi sea. So you only excite near the Fermi level. So you can do analysis under that assumption. And we can do it, more rigorously, but essentially it will probably be similar. Yeah. Okay, so then, I mean, there are several techniques available. So maybe the best one, from the point of view of how well it can work, and can you induce transitions between Landau level, is this method that Dmitry Basov developed, and then various other people, and now it's in the hands of Min-Kun Liu and Stony Brook, and so that's fine. That's just perfect. They see transitions between different Landau levels and in graphene, and that's great. I mean, the only issue with that technique is that the excitation is a sharp tip. Because it's a sharp tip, they're doing scanning, right? Near field scanning. Because it's a sharp tip, it emits harmonics with different Ks, and the largest Ks obviously will dominate. So you will be in this unfavorable regime in which Landau levels will be visible as they are here, but they will have additional broadening that is not under your control. I mean, you need to change geometry somehow for that. And so in principle, it can be fixed, but I think at this point we don't know how to do it. So but I mean, they see very nice Landau levels, and everything is good. But I mean, determining the intrinsic width of Landau level, I think, with the setup as it is now, I think is not doable. But it will improve later. Then there is another experiment in Germany, which is doing different setup, and so there they can apply a more spatial uniform magnetic field, and then so that appeared recently on the archive, and so they do it in graphene, the same way as the other group. And so when they do that, I mean, their technique maybe is less easy to understand as this near field scanning technique, but and also they don't give much information on the paper. So the paper surprisingly provides a very interesting figure, but very little accompanying text. And so if they're watching me, I mean, please write a paper with full description of it. But if you just read what they say, I mean, this is quoting. They're saying that if they take a simple model and they're doing some version of what I just showed you, then they find that there is a systematic narrowing of odd parity resonances, or odd parity harmonics compared to even parity harmonics, and they say that it's beyond the noise level. So they see 1, 2, 3 different harmonics, and if they fit it to a model, they determine which are here, and the odd parity ones are more narrow than the even parity ones, and so that I mean, I'm not sure if that will make you happy. I mean, I would like to see if that's what it is. I mean, it would be nice to have a more clear understanding of what the experiment is doing. But anyway, so they claim that there is some, at least preliminary, that there is something interesting going on. Yeah. So okay. So I think I said all of that already. Maybe let's see if there are questions on that, because I have one more thing to show. Any questions on cyclotron resonance? Yeah.
I just have a question about this Fermi-lit normalized cyclotron resonance frequency, and also earlier you wrote like the plasmon dispersion law.
Yeah.
And on like Fermi-lit parameters.
Yeah.
Can you explain that?
For me, it's not new. It's basically what what we did in that paper that I cited here. I mean, we did it for one harmonic, but then other harmonics are basically the same. And then there is a more recent paper that basically agrees.
I guess I might be confused about something, but I'm trying to reconcile the renormalization of the cyclotron resonance with Cohn's theorem.
Oh yeah, sure. Thank you. Absolutely, yeah. So so because of Cohn's theorem, in a parabolic band, there should be no renormalization, and that's exactly So that's exactly what we see. So this F1 factor is exactly what you need by Landau identity to not have renormalization, because that in Landau theory, 1 plus F1 cancels renormalization of Fermi velocity, and then you lose that entirely. And so you see the renormalization, maybe that's a cleaner way to write it from your point of view. If you look at the renormalization of different frequencies, different harmonics, then harmonic number m equal 1 will not be renormalized, right? So, but I think what I quote is the same result, just written in a more Fermi liquid like notation. If you convert it to what you want to see, then it will look like so. So that it says that harmonics m equal 1 harmonic does not renormalize, Cohn's theorem, and then other harmonics do renormalize. And okay. Cohn's theorem has nothing to say about it.
Okay, thank you.
Yeah, well, thank you. Good point. Good point. Yeah. Okay. Good. So we are okay.
We have 10 minutes left.
10 minutes. Yeah. Good. So let me use 10 minutes talk about one more experiment. Yeah, one more experiment, which I think is pretty cool. So there is this. There are these measurements in constrictions, which see this, viscous-like temperature dependence. But now these measurements can also be used to actually understand the mean free path. And what they do in this paper is that they apply. So they see all of that. That's what we already talked about. But then you can also apply magnetic fields. And what you find is that this increased conductance over here can be suppressed by a very low magnetic field. So you just need to apply a really small magnetic field to suppress that viscous part of conductance. And what this is telling you is that the scattering is really collinear, because, so this is the picture. The way to understand it is that you have a particle, let's say a particle injected from the left lead into the right lead through the constriction, and then, in the stomographic picture, a particle would collide head-on with another particle, generate a hole, and then this hole would run back and go through the constriction, and contribution of particle and hole propagating the opposite way to current will be of the same sign, so it will double in the current. But now, if you apply magnetic field, because magnetic field applies Lorentz force of different sign to particle in the hole, particle and hole will split, and then if you manage to make particle go through, then the whole back reflected hole will not come back, and then you lose the with magnetic field applied, you lose that contribution. And if this mean free path is long, you only need a very small field to kill this contribution. And this is basically what they see. I'll show you more data in a second, but the idea is that because there is a very strong dependence of that peak on the applied magnetic field, you can tell that A, it's really a collinear process, and B, you can estimate you can estimate the mean free path. So you can prove that it's really head-on, a nearly head-on collision. And so from that point of view, I think it's interesting to compare to a few things which are known. It is, you can compare to, so this is based on the article I wrote a year ago for the Journal Club journal. You can compare to cat's eye scattering. Acts exactly the same way. You have an eye, and then there is a photon that comes in, and then in the cat's eye, the back of the eye is reflected. So it comes in, and then it's back reflected from the back eye, and then propagates to you. So when you see the cat in a dark room, that's basically what you see, and it's a pure classical back reflection. And you can call it cat eye reflection, so what I think these experiments prove is that electrons do the same thing. You see cat's eye reflection from 2D Fermi gas, and magnetic field allows you to see that. There is also an interesting, I mean, have to say it because these are very good people, and they invented it in photonic crystals a long time ago. It turns out that one can conjure photonic crystal to reflect photons in the same way, and they call it omnidirectional reflection. Namely, it reflects back from wherever photon comes. It reflects directly back, and so that's that's high-profile work from 25 years ago by John Giannopoulos and Yoel Fink. I mean, all very reputable people. And if you read the abstract, it says exactly what we just talking to each other. Yeah. So it's all well established for photons, and now we have it for electrons as well. And so that's exciting. And then if you now look at it more quantitatively, so you take that peak and zoom on it and ask how actually, I mean, by measuring how wide it is in the magnetic field, you can determine the mean free path. And basically what you find is that from the width of that peak, you see that it's very, very low magnetic field is needed to suppress the effect. That means that the mean free path, going from my point contact to reflection point is super long. They estimated, or we can estimate it, and it more than a micron long, and that comes from this estimate. You see, magnetic field is super low. Magnetic field here, if you determine from the width, is the tip of it is maybe 10 microtesla. 10 microtesla. That's a very low field. Usually magnetic resistance doesn't occur. Strong magnetic resistance doesn't occur at this low field. So yeah, so there is a strong magnetic resistance at ultra low magnetic field, and that translates into gigantic mean free path. And so that's a nice confirmation of this cat's eye effect or omnidirectional reflection effect, whatever you like to call it. Yeah. So I think that's more or less all I wanted to talk about in terms of experiments. Any questions? Yeah, sorry.
Your previous slide, when you keep on increasing the magnetic field, the conductivity goes up, right? So does that mean you go away from this high electron interact regime to like a normal 2D?
Oh, you mean what happens here? Yeah, no, this is not our physics. This is a behavior which is, which experimentalists know about and understand, and they see it in all kinds of samples: high mobility, low mobility. It's something that something due to, I think it's something due to skipping orbits, generate electrons going through the contact. You're asking about this part. I mean, some effect due to electrons going out of the contact and then forming skipping orbits on the boundary. I mean, it's not it's not exotic. I mean, they see it on constrictions of all different kinds. This stuff is exotic. Yeah, okay. Okay, good. So let me skip this part. It's not important. So for conclusion, I think we can just repeat what we said at the beginning, and you know, see if there are more questions. Okay, good. So then, I mean, you can look at it again. So this is actually what a long time. I mean, this profile is real. This is voltage drop. This is voltage drop that we predicted together with how are you a long time ago in Fourier constriction, and there are various interesting features here. You see that like A voltage drops along current, but then also near the corners there is a non-monotonic voltage dependence. And so this was the first indication that you can actually have current flowing one way and the electric field pointing the other way. And so this profile is real. That's all I want to say, and you can relate it to viscous flow. That's it. Thank you.
All right. Clearly, this was not drawn by ChatGPT or any other AI system.
Only one slide,
Which one was
which I skipped.
Oh, that electrons are all drawn by hand?
Oh, that. Oh no, this was before before ChatGPT. So this is from 2017 paper. So it was, you know, long before it was born.
Yeah, it was like amazing art.
But we didn't do it ourselves. I think this was drawn. Who drew it? I think some artist drew it for us. Some artist from Weizmann Institute drew it for us. Is that right? No, I mean, so the plot is yours. I mean, the profile is yours. Yeah, but I mean, the skiers were added by artists.
Yeah, never seen a electron with a palm that.
Yeah.
Right. Any other questions?
Yeah. So for tomorrow, actually, I want to talk about something else. I'm fed up with Hydra. No, I mean, I will talk about Hydra, but a different one.
Well, with that, let's thank the speaker again. I want to remind you today, tonight, there's like public lecture by Renee about making a microscope. So I hope to see you there later tonight.
7 o'clock.
Yeah, 7 o'clock.
And it's a lecture room below.
I think it's a C1B20. That's
Just below us.
Roughly speaking,
Right?
roughly ready.
And the figure of the room factory. It's one of those.